Welcome back. Let's quickly look at how you would go about securing your API, and then we would dive deeper into a specific security problem statement with a lab example. So the most basic of security, uh, features that your ML system should have is to secure the API. So here, um, the comparison would be with the API that we did in week 6, that we built on top of week 7 as well, which is the GKE deployed load balanced endpoint, which we then hit with predictions. Naturally, that's not secure. Anybody who has access to that URL or that IP address will be able to use that endpoint and then go about hitting it. And like I mentioned, a determined attacker can definitely work with various tools to figure out which endpoints are publicly facing, and then within those endpoints which methods like the predict method, etc., are available, and then go after that with various types of input data, observe the errors, etc. So there is quite a bit of a security loophole that's there with our base deployment that we did in week 6. So in this part of the conversation, we're going to dig deeper into how you can go about securing it. I want to say that we're not going to do a lab by itself on securing the API, because there are lots of different options available, and there is no single right answer. There is no single optimal option that exists. So the option that you choose in production in your setting will highly depend on other factors which are not under your control, including, for instance, the information security team, their standards, the IT team and their expectations, etc. While I'm going to give you broad guidance in the next couple of slides, please don't take that as the only foolproof way to get security. This is very much going to be a conversation that will be led by other teams, likely in your company or in the place you work, and your role would be one of a contributor, right, as opposed to a person that's responsible for it. With that preamble, let's dive deeper. So obviously you've got to have authentication. There is no doubt about that. Otherwise, anybody who has knowledge about that endpoint or the IP address can query it. So you've got to have the control that only authorized users of the system access the system. So this by itself is not, like a special topic for ML. Obviously, it's going to apply for any software, not just ML. So broadly, three ways in which you can go about it. One is you use this notion of an API key, and that API key makes it possible for anybody who has knowledge of that key to access the API and then use it for various purposes. The advantage of this approach is that it's very simple. There is no extra overhead associated with verifying identity at the point when the usage is happening, because the usage of the API itself is going to be presumably automated, because predictions are usually real time in the context of larger systems, and at that time you don't want to repeatedly keep asking for identity or waste valuable compute cycles looking for identity. Instead, you use the presence or absence of the right API key as the gate to determine the identity. So the example here is the likes of OpenAI, right? They all provide programmatic access to their GPT based algorithms, so the foundation models, using API keys. Instead of asking you to continuously log in every time you want to use the model, you log in once, you get the API key, and then configure that API key as a configuration secret for your code, and then repeatedly running the code on a daily basis will not result in any extra authentication overhead. Obviously, once a time period has elapsed, let's say 30 days or 90 days, whatever the default is, then the API key needs to be rotated, which means new API key needs to be generated, and then that needs to be fed to your code. so that somebody who has knowledge about the API key continuously uses it is not a problem, right? So you don't want to get into that situation. But at the same time, you're not authenticating yourself every time you make that API request. So that's it, the use of API keys. So it's quite easy to implement, like I said, and we'll show you. Rather, you can implement it yourself if you like, using some techniques we'll talk about briefly. The second method that exists is one of the most production-worthy methods, is to use tokens, either coming from language libraries or you use tokens provided by the OAuth service, as supported by various providers of OAuth as a service like Google, Microsoft, Amazon, etc. So here, the notion of security is more generalized and it's also more foolproof, right? Meaning, unlike API keys which rotate once in 30 days, where if the API key happens to get leaked for whatever reason or gets visible to nefarious users, then they can use that API key until that 30-day window elapses. So that's a problem. Whereas with OAuth and token-based authentication, it verifies identity directly with the end user using sometimes even second factor, third factor authentication mechanisms. Like for instance, you'd love to use an app to you know prove your identity by choosing the right captcha or the right numeral that's showed in front of you, or sometimes you'll have to enter OTP information, etc. So all of that is OAuth 2.0 mechanisms. Most production systems that are end consumer facing are best secured using OAuth 2. The third method is using service accounts, where you delegate the identity itself along with the access to a service as a named account, and that named account becomes a privilege that various other services that want to access this named service can use by adopting that named account for a time period until the access is finished. So we used service accounts quite extensively in the week 6 Kubernetes setup. If you remember, telemetry access was what it's called. We used telemetry access in week 7 as well, by the way. Or maybe it was in week 7 that we used primarily. Anyway, so service accounts are used very commonly within cloud infrastructure. So GCP services calling each other, etc., etc. So for production usage, I would recommend OAuth 2.0 plus token-based authentication using JWT. You can protect the API that you used within GCP itself if you continue to use GCP as the vehicle of choice for deploying your models using IAP, identity aware proxies, or you can set up OAuth 2 verification using a service like API Gateway, which is again a Google Cloud provided service. If you don't want to use API Gateway, or if you want open source options for it, there are quite a number of popular tools. Kong is one of the most popular tools, lightweight, but at the same time really flexible and scales well. It's good for massive scale deployments as well as easy to start deployments. So super popular. It's got various kinds of plugins, like for rate limiting, it's got a plugin for token-based authentication, for ACLs like access control lists, IP restrictions, so that you say that this is the whitelisted set of IPs that have access to this particular service. It's got native Prometheus exports so that the matrices get published into a Prometheus server, etc., etc. So Kong is very popular, used for enterprise grade setups, etc. Ambassador is another example in the open source world, great for Kubernetes based microservices, especially on GKE. Nginx itself is an extremely popular open source package. It's used as a load balancer or a proxy, reverse proxy, but you can also use it as an ingress controller. So it serves multiple purposes. Again, for container based systems, it's a great add-on. And then traffic is another example. So for typical uses, I would say just choose between Kong and Nginx. You would not go wrong. Okay, with that said, let's get into our lab. in this, we're going to poison our cats and dogs. I'm joking, of course, but I'm going to use the cats and dogs classifier that we started off in week 2, use again in week 4, and we're going to go deeper into how we're going to introduce this, security attack of data poisoning and see the impact that it causes on the model itself. So for this, let's go into our model. I'm going to be switching to my Safari page. Yep. And go to my Google Cloud Console. So if you remember from week 4, we set up GitHub repos and all of that for the cats and dogs classifier. So hopefully you've got that already in your GitHub profile. So in my GitHub profile, I've got it as MLOps week 4. So I'm going to use that GitHub profile as a starting point. So let's go about doing it. I'm going to use Cloud Shell for this. Let's go ahead and activate. As before, I've got a bunch of these commands already set up. So let me increase the font. There we go. So let me actually get rid of week 8 here and start again. Okay. So I'm going to okay. So within week 8, I'm going to get this MLOps week 4 repo that we created in week 4, as the name suggests. I'm going to do a git clone, bring it in. Great. Let's go inside and see what's there. Okay. It says MLOps week 4. Okay. Yeah. So this got the train.py file, which trained the cats and dogs classifier. But if you remember what we did in MLOps week 4, which was actually building on top of week 2, we used DVC to control for the data. And when we did that, the data was not copied over into GitHub, whereas DVC was responsible for it. The code was copied over to GitHub. So let's firstly, check whether we've got the right username and things like that. Config. Okay. Okay. Remote origin. Oops. Yeah. So I've got both my fetch and push pointing to the MLOps week 4 Git, which is good. So now the data is not in GitHub. Where is the data? That's actually in week 2 within example versioning. If you remember that, there is a data folder, and that data folder has the data associated with it. We had created the DVC files at that time. How do we know all of this? So this is there within the DVC cache, right? So in order to use that same data, just like we cloned the GitHub repo, we've got to now ask DVC to use the DVC cache that was created in week 2. So that's a local cache. Now in production, obviously you're not going to use local caches because those are susceptible to get lost, to be lost. So you would use instead the caches that are deployed in, let's say, GCS or other kinds of shared storage systems which are persistent. Nevertheless, we're going to, use DVC for pointing it to that local remote. So that's what we do here in this command. So we ask DVC to use a local remote option, not like a GCS based remote. And where is the local remote? It's in the path. The path is DVC cache that's present in our week 2. So let's configure that. Okay, fantastic. And the best practice we spoke about before with the Git flow, since we are going to do data poisoning on top of this code base, I'm just going to create a separate branch on top of which I'm going to do all of this work. And since I'd already used week 8 as a branch in preparation for this lecture, I'm just going to create another branch. Let's say week 8 version 2. There we go. We've switched to this new branch. So right now there should not be any changes except for the .dvc file. Yes, which is good. So now what I want to do with data poisoning is to introduce certain poison in the data. The way I'm going to do the poison introduction is by looking at how the labels can be manipulated. So let's go back to the base data itself. This is the base data for 2000 images. How did I get this information? You can get this information by going to your GitHub file. If you remember the sanity test that you did back then, that was like 3 weeks ago, whenever that was. In that, there was a CML report that you had created as part of week 4. You can click on that CML report. The CML report would have actually printed out the metrics from that training run. Alternatively, you can just go take a look at the metrics training run directly in the GitHub repo. Doesn't matter. Just take a look at this and then plot it. You'll see the movement of the accuracy as the epochs have changed. So each epoch, you're going through all the training data. The accuracy and the loss corresponds to the training accuracy and the training loss. The val accuracy, val loss corresponds to the validation accuracy, the accuracy on the validation data set. So for a good model, you've got both training accuracy and the validation accuracy continuously increasing, ideally, with validation loss kind of stabilizing after a point in time. And with your base model, these are the matrices that you see. So if you plot it, this is how it comes to. The training accuracy, validation accuracy is fairly okay. It's 90 plus. The training loss obviously keeps going down for every epoch. The validation loss keeps fluctuating. It's not the ideal. There's a bit of overfitting that's going on. But that's our base run. So let's introduce controlled poison, right? So what is poison here? I'm going to just mislabel data, right? That's my example of poison for this problem statement. So the way I'm going to do it is by moving an equal number of cat images to the dog folder and dog images to the cat folder. Why an equal number? Because I don't want to modify the code, right? The code is expecting the same vector size for both classes that are possible in this classifier problem. As a poison introducer, as a person who's poisoning the system, I can't have access to the code. Instead, I do have access to the training data. So therefore, let's go change that. The other thing to keep in mind is that I don't want to touch the validation data, because the validation data is what's going to be used for validating the model. And that's going to be a benchmark to understand whether the act of introducing the poison changed the validation significantly or not, or changed the model accuracy. So change the training data, don't touch the validation data, use the validation data for benchmarking. I'm going to define a poison metric called as percentage corruption. Our base image sample size is 2000 images. So on top of that, go make some change, right? So you can think about this experiment as one of introducing noise or introducing poison, doesn't matter. But basically there are multiple, parameters are possible, multiple levels to which the poison can be introduced, right? Obviously, no poison introduction is just, no images changed. You change a bit of, images, like 20 images on a base of 2000, that's 1%, going all the way up to 7.5%, which is 150. At 10%, you start to really significantly impact the model. In fact, we're going to do an experiment at 5% and show and see what the model output looks like. I would strongly encourage you to try out other, numbers here as well, right? Like go up to 10% and see what the if 10% of the model data is mislabeled or poisonous, how does it impact the model output in terms of accuracy? Go ahead and try that out. So for now, I'm going to focus on this experiment of 100 images because I'm going to need an equal number of cats and dogs to be flipped, right? I'm going to just split the 100 as 50 and 50. So how am I going to do that? Where is the, yeah, there we go. So within my data, yeah, so I've done a DVC remote. Okay. Okay, so let's go to our data. So I'm just going to go to my cats folder. That's, yeah, so this is the folder where I want to do. So I'm going to just execute a simple Linux core util command. So what I'm doing here is I'm creating a temporary directory into which I move images numbered cat1 to cat50, right? And I'm making sure that I'm processing only 50 images, visually inspecting the output. So right now the temp directory should have 50 images. There we go. We can do a quick count. And these 50 images are what I'm going to move to the docs folder. Okay. So now if I do a ls in the cats folder, it should be 450. There we go. 451 is just the temp directory itself, which we want to remove. So let's just remove that. Great. So now I've moved 50 images from cats to dogs. Let's do the vice versa. So here again, I'm going to just do the same command. So instead of cat dot $I, I'm going to do dog. Yeah. So then move all of these into the cats folder. There we go. So now if I look at, yeah, let's remove temp. Okay, good. Okay, so now we've got cat 9, cat 8, etc. all the way. Cat 50 is also here, and then the rest of it is dog images, right? Likewise, in the cats folder, I've got a bunch of cats, but I've also got a bunch of dogs, small bunch of dogs. So I've got my data worked out correctly. So let's go back to week 8. And now, because I've done the DVC remote mapping, the data file is appropriate. So let's start executing the code. So let's do this. Let's create the virtual environment. We'll activate it. Yeah, by the way, in case you're wondering, how do I get to the front of the line? I'm just doing Control A. So these are all Linux util tricks that you should know. Anyway, pip install, let's go install this environment. no space left on the device. That usually happens when yeah, because it's a cloud shell, we don't really have too much space to play with. Let's see whether we can reduce the space. Yeah, in fact, I've got a copy of MLOps week 4 here. That's probably why. So let me just delete the. Yeah, okay. So just to clean up the space, I'm going to activate this environment so that I'm in the right place. Okay. Pip install. Yeah, so this environment already exists, so we can just use this. Okay, so I've got my data worked out. So let me now do a train. This training exercise will now pick up the poison data and run with it. So we'll give it a few minutes. Great, the model has made its run. Let's ensure that the files are updated. There we go. Metrics.csv got updated. Model.weights.h5 or both of those got updated. So let's add those to the dvc file. Okay, good. So we'll add okay, that's been added to Git. So now we're ready to commit to Git this poisoned run, so to speak. Okay, good. So let's ensure that we are all operating in the right branch. So we're operating in the master branch. Okay, no problem. If you've done the Git checkout correctly, you should be operating in the checkout branch. Anyway, in my case, I'm done it in the master branch, so I'm going to go ahead and finish this experiment. But hopefully, you are operating on the week 8 2 branch, and then you're moving ahead with it. Okay, so I'm going to tag this. Oops. Okay, good. So now I'm ready to push it into Git and get the GitHub actions to run. So let me do that. Oops. The password would be okay. So that's done. Let's go back to GitHub. Take a look at the code. We've got the commits now here, poisoning 5% of the input data. Good. So let's go execute the sanity test action on it. So I'm going to run workflow on the master. Yeah, that's where the commit happened. Okay, so it's running right now. So as before, once it has finished running, if you take a look at the CML report and look at the comment within it, you'll get to see what the set of matrices look like for the poison run, and then you start comparing the two, the poisoned versus the clean. You'll see that um, the poison run actually has similar improvements in the training accuracy. It's broadly been it broadly shows that it's okay. So the model tries to memorize whatever is given to it, including the wrong labels, which is fine. But then on the validation set, um, the uh, the loss and the accuracy starts to show. So the accuracy for the validation looks okay, even though the poisoning was happening, but the loss makes it go through significant ups and downs, right? So this shows like a bit of confusion happening given the contrarian examples that the poisoning introduced. So that's with 5% of the data. Imagine now with 10% of the data, how much of that poison will result in the model's accuracy or the performance to change. So that's for you to try out. So with that, we close this lab on data poisoning. We spoke about other security methods and other security problems also. To dive into details of it would require, like I said, more advanced coursework and structure. Like for instance, setting up adversarial examples is a entire field or art in itself. There are techniques called as, I think, fine gradient, sign method, etc. What they do is they look at the network architecture, look at places where the weights are significant, and look at ways in which you can tune the weights in such a way that the threshold for activation gets turned on or off based on the adversarial example that you want, or the adversarial behavior that you want. So it's a fairly sophisticated way to create examples which are slight perturbations in the input data, but it requires knowledge of the network, knowledge of the kind of problem statement that you are dealing with. That's why I'm saying it's fairly more advanced. But the fact that it's possible, and the fact that it's possible algorithmically, is something that you should think about when you start working on ML systems yourself. Other examples like securing the model endpoints, the infrastructure, all of those, like I said, is very closely tied with the infrastructure security, IT security, information security teams, and usually those teams take the lead, and the ML teams will be playing a contributory role. Whereas things like data poisoning, model artifact protection using encryption, those are well within your control, and you should absolutely pay attention to those. Great. So with that, we close this week's lecture on security. In the next week, we will dive deeper into two specific aspects of security and governance, which is explainability, drift detection, and how do you do compliance-based monitoring. Thank you.